Dr. Lyman, I'll pass it over to you.
Great, thanks. And if the connection starts getting a little wonky, let me know as soon as possible. I may turn my video off. All right, let's try to get this going. All right. Okay, can you see my screen?
Yep.
All right, so thank you for being here. I appreciate it. I was already introduced, so I won't go through this, but the title of my talk is Nuclear Power Really the Safest Form of Energy is something that I feel needs to be addressed, because if you look at my title, Director of Nuclear Power Safety, if this is actually a true proposition, then one might wonder what I'm actually doing in my current position and might as well retire. But as I will discuss, I think it's actually a little bit more complicated than some people seem to make out. So the bottom line is nuclear energy may have benefits for carbon mitigation as a low carbon electricity generating source, but can't really be overlooked. The safety risks are dominated by the potential for catastrophic accidents. And here I think I'm stopping my video. That this is one of the unique things about nuclear power plants is that they do have the potential to unleash vast quantities of radioactive materials into the environment, long-lived radioactive materials, as the world has seen with Chernobyl and Fukushima. In addition, nuclear power plants are potentially vulnerable to sabotage and military attacks. And no matter how safe the plant is as it looks on paper with regard to accidents, if someone knows what they are doing, they can unravel all the safety measures that keep nuclear power operating safely. And if you have a nuclear power plant that finds itself in the middle of a war zone, as the world saw with the Zaporizhzhia nuclear plant in Ukraine, currently occupied by Russian troops, then the concern is really crystallized, the potential that a nuclear power plant could end up either voluntarily or involuntarily or deliberately or indiscriminately as the target of a military attack. And nuclear power plants simply were not designed to withstand that kind of damage. So if you don't deal with these challenges effectively, then the nuclear power may end up taking itself off the table. In Japan, after the 2011 Fukushima accident, essentially the entire Japanese nuclear power plant fleet closed down for many years. They're only starting now to haltingly start up a fraction of that fleet, but it really was a blow to Japan's nuclear power ambitions. And it's not clear how many more accidents like that around the world it would take before the public worldwide really sours on nuclear power for good. So it's really in everyone's interest to make sure that nuclear power is safe. And the regulators are the bulwark against some of industry's worst ideas. Industry is constantly pushing to weaken regulations, both for operating plants and for licensing new reactors, in an attempt to reduce the cost of building and operating nuclear power plants, which still is very high in comparison to many alternatives. And the industry has fixated on the regulator, scapegoating it for its own problems, and is consistently trying to water down the safety and security regulations that cost it money. Now, nuclear energy, despite all its problems, it is experiencing a resurgence of political and public support around the world, and I have some ideas why that's happening. We don't have to get into that, but many nuclear advocates are capitalizing on its low carbon attributes to call it clean energy, including, for instance, the Biden administration. Now, used to justify calls for relaxed safety security standards and just talking. But it's pretty to characterize an disorder as a matter of course through normal operation, generally large Sorry, is there a problem?
So sorry about that. I think
Um,
that's an issue on my
Yes.
end, but
Okay. So some are claiming that not only is nuclear power safe, but they're saying it's the safest form of energy, even compared to renewables. And I don't feel that either public or environmental health are being well served by this kind of misrepresentation. Now, there are people on both sides of the debate who may misrepresent the scientific evidence or look past it to either downplay or exaggerate the risks. And I don't think in either direction that's particularly helpful. But if you are going to believe in the precautionary principle, and when there's uncertainty with regard to a question, an issue that could affect the environment and human health, it really warrants erring on the side of caution. So I do feel like those who are who are more cavalier about the potential risks of nuclear power and are denying that are really potentially endangering the public health with their approach. And they really, I believe, are in the same category as, the other hazardous industries, the tobacco industry, the other deniers who try to greenwash their products. And, it doesn't, if it goes beyond what the scientific evidence shows you, then it's not really doing a service to public health. Now, nuclear power poses a wide range of risks to the public. First of all, as nuclear power plants operate, even normal operation, they are going to be leaking radioactive materials into the environment. If it's running properly and meets the regulations that restrict those types of effluents, then those risks are relatively low. But that's in some cases a big if. Also, the nuclear fuel cycle, that is not the entire cycle from uranium mining and milling to fuel production to waste management and disposal. There are releases associated with those operations, and that varies a lot depending on the details of the system you're talking about. But you can't discount those either. Then there's the release from the accidents that we just talked about. And generally, this is going to be the biggest contributor, but it's not the only one. And then, as we mentioned, terrorist attacks can subvert safety systems, and you need to address them independently from what from what you do to protect against accidents. Then, of course, occupational exposures. Workers at nuclear plants and throughout the fuel cycle are going to be exposed to radiation as a part of their jobs. Those historically were a lot higher in the early days of nuclear power than they are now, but they're not zero. And if there isn't stringent attention to and maintenance of keeping those low, then mistakes happen and workers get overexposed. So you can't ignore those either. Then finally, there are the issues with nuclear waste, which is essentially forever. And even if it's packaged or stored in the near term in a way where it's not posing a great risk to the environment, if you don't maintain it. So let's cut to the chase. All right. So Bill Gates, among many others, have been citing this factoid that nuclear power is the safest form of energy. And Bill Gates is invested now in nuclear power because he has his own company, which is developing a new type of nuclear reactor. And he has gone all in his nuclear evangelism. So most of the people who are claiming that nuclear is the safest form of energy point back to this one website called Our World in Data. And they, in 2020, they posted this graph here, which claims to estimate the number of deaths per terawatt hour of electricity generation, and a large nuclear power plant generates 8 to 9 terawatt hours a year, just to make that clear, of energy, electricity. And so according to this, the fossil fuels, coal and oil, are the most damaging to health. And this it's hard to disagree with, given what's known about the impact of fine particulate matter on respiratory and cardiovascular health and mortality. So that's not really in dispute. But when you get down to gas, now I don't want to apologize for natural gas, and UCS is a big believer in the transition away from fossil fuels, but gas generation doesn't generate the same kind of particulate matter, and I guess you can see that reflected here. But if you go further, you see that according to this, that nuclear power is about the same as wind and solar with regard to the number of deaths per terawatt hour. Okay, so is nuclear power really as safe as wind and solar energy? So when looking at something like this, things to consider, anyone who has some critical judgment might wonder, is this really a meaningful parameter or metric for comparing the health impacts of these very different sources? And those health impacts are very different in temporal and spatial the way they occur. So can you really reduce all the complexity of trying to compare the life cycle impacts of these energy sources into this one metric, deaths per terawatt hour? I would say no, but just raising questions about it. What about disease that doesn't kill you? Now, of course, that's going to be cross-cutting as well, but is it reasonable to leave it out? What about when you just look at some broad average of an impact like this over all of society? Are you taking a look at the disproportionate impacts and the communities and populations that are disproportionately affected? Or does this just wipe that out? Then you may ask that you're comparing routine emissions from one energy source to accident impacts from another. Does that make sense? But also, this is looking in the past. And is it reasonable to extrapolate from the past to the future? But if you look past all these methodological problems, is the number right? Is it consistent the way this number was derived? And what are the uncertainties? And just looking at some of the other parameters, there's broad disagreement with some of those numbers from the literature. For instance, a study that came out in 2019 for the US found that natural gas is really only 0.2 deaths per terawatt hour, so it's a factor of 10 lower. And generally try to think that these numbers within a factor of 10 or maybe even 100, I think is unreasonable. But moving on, let's look at that value for nuclear power. And just to reiterate what it was 0.03 deaths per terawatt. So our world in data, so our world in data, which was that website that Bill Gates and so many others are pointing to, claims that the consequences of Chernobyl and Fukushima were fully taken into account. But taking a closer look at what the author actually did, you find out that a lot is left out and things are put in that may not really belong there. So, for instance, the author only looked at the thyroid cancers among children that are attributed to Chernobyl. And that is one of the clear signals. One of the clearest signals of the health impacts of the Chernobyl accident was this very unusual thyroid cancer in children, where the signal was so great that it was hard to deny a cause and effect. And there's certainly statistically significant excesses. But thyroid cancer has a very high survival rate. So Ms. Ritchie just took the number of thyroid cancers and the survival rate, and that's the death toll of Chernobyl that she used. Now, with regard to Fukushima, she didn't consider the potential for any deaths that would be caused by radiation exposure from Fukushima because none have been registered yet. Instead, she looked at the evacuation of 160,000 people were evacuated in the chaos following the tsunami, the earthquake, the tsunami, and the nuclear accident. And there were quite a significant health toll from these evacuees. So a lot of people are claiming that the only consequence of Fukushima, the only negative health impact, left where they were. And I have some things to say about that later. But anyway, she included those, and they probably shouldn't have been. But in any event, the bottom line is that Ms. Ritchie ignored the potential that low-level radiation exposures would cause cancer, and buried in that assumption is this belief that there's a threshold that ionizing radiation below a certain threshold will not cause any harm, that there'll be no detectable cancer increase. And some people even believe that low-level radiation is good for you. And this is not consistent with the scientific consensus. So as I pointed out, so the most obvious impact of Chernobyl was the excess thyroid cancer among children. But that doesn't mean that there are no other health consequences. And fact is that ionizing radiation exposure and its impact on human health is pretty well characterized. There are still uncertainties, but it's one of the best studied carcinogens. And so that exposure, even to low levels of ionizing radiation, is associated with harm. And but that may not show up in an epidemiological study if you don't expect, if that signal or the actual doses were not large enough to give you the kind of statistically significant excess that you saw with a child with thyroid cancer. But it doesn't mean the cancers aren't there. It just means that the signal isn't big enough to be detected above the background. But some people tend to believe that if the signal isn't there, then you can forget about it. But in this case, you can't really forget about it because there have been predictions extrapolating from the calculator estimated doses resulting from the Chernobyl accident from 4,000, potentially 4,000 cancer deaths in the former Soviet Union alone, which was a result of a joint report from the World Health Organization and the International Atomic Energy Agency called the Chernobyl Forum, itself a controversial number because it didn't look at the exposure outside of the former Soviet Union, even though most of Europe did receive fallout and some radiation exposure from Chernobyl. In fact, it did circulate around the entire northern hemisphere. If you consider the estimates of that collective radiation dose around the world, then you could expect tens of thousands of cancer deaths over decades as a result of Chernobyl. Now, Fukushima was a smaller release than Chernobyl, about 10 times less radioactivity, and the potential health consequences are proportionally smaller, but not zero. So if you look at the linear no threshold approach for estimating the cancer deaths from low-level radiation exposure, and again, the atomic bomb survivor study, this very large and long-term cohort study called the lifespan study, has shown consistency with a linear no threshold model. That is, that the risks of solid cancer are proportional to the dose, and there's no threshold below which there's no effect. Now, the problem with the lifespan study and that second bullet is that the statistical power of the study isn't enough to rule out a threshold below certain doses, but there are other studies, including more recent ones, that are pushing that that value down. And there's also, there's good fundamental biological reasons for believing that there is no safe dose of ionizing radiation, because even a single radiation track across a cell can damage the DNA. So the consensus is that you do assume for radiation protection purposes that there is no threshold and that it's essentially linear. Now, the quantitative estimates, the most recent ones coming out of the United States National Academy of Sciences, which has done long-term studies, found that the mortality associated with low-level with radiation exposure was about, should be 6% per sievert, not 0.06, or it would be 0.06 times the sievert. Sorry, that's an error there. A sievert is equal to 100 rem, which is a representation of the absorbed radiation dose in tissue, taking into account the differences in different types of radiation and their impacts on the body. And these values, which are called risk coefficients, are adjusted in the Beer 7 study from data from the lifespan study with a fudge factor of 1.5, which is called the dose and dose rate effectiveness factor. And that is taking into account what some people allege, that at low doses or low dose rates, ionizing radiation exposure is less effective in inducing cancer than at high dose rates. But there's not a whole lot of evidence for that. In fact, a large analysis of radiation workers around the world has not found evidence for this factor, in which case the coefficient would really be, and again, that would be about, you would multiply that by 1.5 to get about 0.1 per sievert. Now, the UN has a specific committee on the effects of atomic radiation, which has been around since the early days of nuclear energy. It's done studies over the years to try to estimate, again, these global collective doses from nuclear power. And in one of their earlier studies, they tried to estimate the global impact, the total dose, and they found around 600,000 person sieverts. And again, these are pretty rough estimates. Within Europe itself, about 2/3 of that, so 400,000 person sieverts. Now, the UN UNSCEAR committee also did an estimate of the Fukushima accident, and estimated the collective dose in Japan would be about 48,000, which is roughly a factor of 10, less than what happened in Chernobyl. But if you assume that all those were low doses and you do apply the dose rate, a low dose reduction effectiveness factor, you would find Beer 7 would predict about 27,000 cancer deaths in Europe and Japan from both accidents. And if you don't use that fudge factor, it would be around 40,000. And so if you do the math, there were about 85,000 terawatt hours of nuclear energy generated since 1971. That works out to 0.32 to 0.48 deaths per terawatt hour, so something like 10 times the number in our world and data. And so this is still lower than what that found for natural gas, but it's 10 times greater than wind and solar. And I don't present this data as any kind of, definitive number. Again, I think all these, this type of analysis is pretty treacherous, but it really does illustrate that, you can manipulate these numbers depending on your assumptions and get pretty big differences. So what about other sources? So if you're looking at those other exposures that I was talking about, for instance, the routine emissions, occupational doses, nuclear fuel cycle, UNSCEAR has also tried to estimate the global, dose commitments from these activities per, again, unit of electricity generated. And one of the interesting observations it made is that since radioactive materials, many of them have very long half-lives, if you put them into the environment, they're going to be around a long time and they'll accumulate. So the doses actually will increase over time. And if you take that into account, then you get, again, much larger overall contributions to or detriment to public health. So I have some of the numbers here for normal operation. Unskier found, again, this deaths per terawatt hour comes out to something like 10 times less than the accident doses that were predicted in our world data, or 100 times less than my estimate for the accident doses. And same with occupational doses. So smaller, but not insignificant if you add them all up. And again, if you look at the contributions from these isotopes that stay in the environment for hundreds of thousands of years, and it's arbitrary when you decide to, how long you decide to look out into the future. But I mean, if you apply logic, you need to worry about those even tens of thousands of years in the future, and the numbers keep growing. So again, you could have a pretty large contribution just from the routine emissions from nuclear power if you look at those cumulative doses out over time. So again, depends on your assumptions, and you can get pretty wide swings in your estimates. Now, this was historical. Again, you can always argue, well, why should these one-off accidents like Chernobyl and Fukushima say anything about what's happened, what the risk is today or in the future? But there are studies that are trying to power plants operating today. And even though accident risks are generally believed to be lower, much lower than they were decades ago, they're still not insignificant. And no one, they might be lower, but no one really knows how low they are today. And let's just take the Seabrook nuclear plant in New Hampshire, which again would generate about 9 terawatt hours a year of electricity. There are, in 2000, which is the year when NextEra based its license renewal application for the plant on, there were over 4 million people in the 50 miles. That includes the entire Boston metropolitan area. NextEra calculated in its license renewal application that the possibility of a core damage accident, that is something like what happened at the 3 Mile Island reactor in Pennsylvania in 1979, where the core was actually damaged, but the containment held. But they predicted that type of accident could happen at Seabrook about once in every 81,000 years. But the likelihood of a large radiation release, that is, let's say something like Fukushima, where not only were reactor cores damaged, but there was significant leakage of radioactive material from those cores into the environment, that NextEra calculated that was down closer to 1 in 300,000 years. So these are small numbers, right? But if you actually do the math, again, based on NextEra's estimate for the total collected dose within 50 miles from a large core melt accident, that would work out to about 0.0025 deaths per terawatt hour, so even lower than what our world data predict. But turns out that NextEra's numbers might not be so good, and the Nuclear Regulatory Commission has been for more than 10 years trying to do the most definitive study they could think of to look at all the risks associated with a nuclear power plant, and they call that the level 3 probabilistic risk assessment. Not only looks at the risks when the plant's operating, but also when it's shut down, which are not insignificant, looking at both internal events like pipe breaks, external events like earthquakes and floods, looking at the impact of one reactor on another. So many plants have multiple reactors on site, but the assumption is usually that only one of them will go bad at a time, but maybe one will affect the others, as was seen at Fukushima. And also, what about the radioactive waste stored on site? We know that there's every nuclear power plant is storing essentially all the spent nuclear fuel that it's generated through its course of operation. That is also potentially at risk. So this level 3 study was supposed to look at all those things, and it still is not complete. But part of the results are out already. And if you look at the results and the Vogel station, that is the two original Vogel units in Georgia, were the basis for this level 3 study. And by coincidence, it happens to be the exact same design as at Seabrook, a Westinghouse large dry containment 4-loop pressurized water reactor. And so if you assume that maybe the results from the level 3 PRA are also going to apply more or less to Seabrook, you find out that the numbers that they are getting, the risks are much higher. So for instance, the core damage frequency, that is this likelihood of a 3 Mile Island-like event, is something like 12 times what NextEra calculated for Seabrook. And the possibility of a large radiation release is like 32 times what was calculated for Seabrook. And that's because they were looking at the potential. And if you have a severe nuclear reactor accident over time, even if the containment doesn't breach right away, over time, it's going to pressurize and eventually going to breach. And if you look at that risk, it's a lot higher than what most studies currently assume. So if you look at these revised values, you find out that the deaths per terawatt hour from an accident at Seabrook could be up to like 0.12, which is again higher than what our world data found, higher than gas, higher than higher than wind, higher than solar. And you know, again, when you do these calculations, it's pretty treacherous. There's just lots of uncertainties, and there are lots of ways to gain the numbers to make them look as low as possible. But I've spent a big part of my career trying to tease those out and look at where those assumptions are unreasonable. And I know that these kinds of studies could underestimate the actual risk by a factor of 10. They could also overestimate. But if we're worried about being conservative, the worst case, then these numbers could be lower by easily a factor of 10. And then you're talking about an energy source that is many times, more than 10 times higher than wind or solar, and even higher than natural gas. So, also waste. Now, I mentioned spent nuclear fuel is stored, much of it in pools at current reactors. Those are also vulnerable to accidents, and the potential consequences of a fire in a spent fuel pool could be enormous. And those are generally not taken into account in these earlier estimates, but I just say that studies would find that you could have significant numbers of additional fatal cancers from the release of a large amount of cesium-137 from the spent fuel pool. And if you then consider that type of event, which generally would only be caused by a large seismic event, could also be caused by a terrorist attack. And then if a terrorist attack is involved, you can't really predict how frequently it's going to happen. You can't put a number on that likelihood of a terrorist attack. So the events are uncertain, but the consequences have been estimated. So here's a study that looked at what if there was spent fuel pool fire at the Peach Bottom nuclear plant in Pennsylvania. And the red area is essentially the area that was triggered a mandatory evacuation after Fukushima. So you'd see that in the entire Philadelphia metropolitan area, as well as Wellington, New Jersey, would be potentially subject to mandatory evacuation. And consequences could be experienced as far away as Cape Cod. So just the amount of radiation stored in these pools is enormous. And if you worry about what could happen that would make nuclear power, look even worse. Now, we're only talking about cancer deaths here, but there are other health consequences of ionizing radiation exposure, some of them just starting to emerge. And one is cardiovascular disease and mortality. And a recent study has estimated that the potential mortality from low-level radiation exposure due to cardiovascular disease is a significant fraction of that of cancer, maybe 30%. And it depends really on where you are, because to develop absolute rates, you have to know what the background rates are, and that varies a lot from country to country. But generally, it could be 30 or 50% additionally to the cancer mortality. And that means that all these numbers are low by, another significant factor. So the story is still not completely told for what the impacts of ionizing radiation are, and for what the impacts of nuclear power or the risks of nuclear power and the potential to expose people to ionizing radiation are. So to try to conclude that nuclear power is the safest form of power generation with the available data today is treacherous. First of all, don't trust data presented without any error bars, and that includes what I gave to you myself. And also trying to oversimplify these kinds of complex analyses with these simple factoids is just not appropriate. And I don't know if Bill Gates has done any thinking about the quoting this factoid, but he really should. And frankly, if you mislead the public on nuclear power's risks, that's going to contribute to bad public policies, such as weakening safety regulations, because nuclear power safety record would likely be a lot worse if the stringent standards for licensing and oversight that are in place today didn't apply. So there's a real risk with this move toward weakening nuclear power safety and security regulations to make it easier to license and deploy nuclear plants, even in densely populated areas. That's not a good direction to go, especially when we still don't know, when there's still so many gaps in our knowledge about the impact of nuclear power on human health and the environment. So I'll stop there and be happy to take some questions. Thank you.
Yeah, thank you so much, Dr. Lyman. I'm so glad we were able to see the rest of that presentation. That was really, really interesting. And I appreciate your time and flexibility tonight to get us that important information. So we have a few questions in the chat here. So I'll invite folks to unmute and ask their questions just to make it a little bit more interactive, because there's not too many of us anymore. So Bob Dewey, do you want to unmute and ask your question? If not, I can read it as well. I'll just go ahead and read it. So did the authors of Our World Data include, oh, go ahead, Bob.
I figured it out. I just couldn't find the button.
Oh, no worries.
Yeah, you're here. Thank you for this, Dr. Lyman. This has been terrific. If not a little exciting early on, but do the authors of that One World Data, do they include deaths from people who mine and process the uranium? And what is the morbidity and mortality rate in that population?
Yeah, so no, Our World Data didn't consider that or any of the fuel cycle impacts. The UNSCEAR study that I referred to does, but again, it's when you have to separate historical impacts from future impacts, because of course things in the early, the dawn of the nuclear era, especially when uranium was being mined to support the nuclear weapons program, there was, a lot fewer precautions being taken at that time. But the major impacts are the effect of inhaling alpha emitters among the underground uranium miners. These are the radon daughters that are well known to cause lung cancer. And there are crude estimates. There's certainly been epidemiological studies, going back, of course, to the Middle Ages. One of the first epidemiological studies was of workers in mines in Germany. But it's hard to put a number on it. Unscared did, and I did show that in my slides. That did include the uranium mining and milling, which would be about, again, in this ridiculous deaths per terawatt hour, about 0.01 to 0.02, something like that. But the other impacts are harder to measure, and if you're living downwind of a uranium tailings pile that isn't properly capped, it's going to be emitting radon continuously, essentially forever, and those radon's going to decay to those radon daughters. They're going to drift. People are going to inhale them, and also eventually radium in the groundwater if it's not properly contained. And it's really hard to put numbers on those. Not that people haven't tried, but even so, probably still smaller than the very high doses that occur when a nuclear power plant has a severe accident close to densely populated areas.
Thank you.
Thank you. Deb, I see you have a few questions in the chat. Do you want to unmute yourself and go ahead?
Sure. Thank you so much for this presentation. It was really interesting. I had two questions. First of all, I'm going to acknowledge that I'm guilty of reading the Bill Gates book and getting really excited about nuclear energy as the solution to all of our problems. So I'm just wondering two things. First of all, in your position, knowing what you know about nuclear energy and other forms of energy, obviously it does not make sense to weaken safety standards. Nobody really wants that. But do you think we should be using nuclear energy as a bridge to truly having all clean energy in this intermediary period while we're waiting to, be able to go green? And then my other question is less interesting, and you talked about other things about it later, but what do you think would be a good way to compare the safety of fossil fuel sources to nuclear energy?
All right, well, I'll start with the second one first. Since the only way to do it is to really define clearly, what you're talking about, and is it really, are these really directly comparable? So limiting the scope of the metric maybe to something that would be useful if you actually wanted to address risk. So instead of looking at this broad brush, these deaths per terawatt hour, to focus on those aspects of nuclear power and nuclear fuel cycle, look at who's being affected, look at how much, and and address those risks in a meaningful way, and also acknowledge that that we have agency over what happens in the future. It's not the fact that if you're comparing, and again, I don't want to praise fossil fuel, but again, to some extent, it's the lack of regulation over fossil fuel emissions that have contributed to its health detriment in the past. You spend the money, you can probably mitigate that to a large degree, and the same with nuclear power. So it's really a matter of where you want to devote your resources best, and that is really a larger question of energy policy. And I guess I've drifted into the first part of your question there. We don't take a position pro or anti-nuclear power, but we do believe, it has to be safe and secure, and that there's no imperative for nuclear power. It has to hold its own against its competitors, and doesn't deserve special treatment, doesn't deserve special subsidy, and doesn't deserve any slack when it comes to its potential safety risks. There's no urgency to maintaining nuclear power if there are alternatives that work better, are more economical, or safer. So there shouldn't be any essentially pre-assigned role for nuclear energy. It needs to prove its own weight, but also you can't, again, try to compromise on safety and security. You have to factor what you need to make it safe enough into its ultimate cost, and that really should be one of the deciding factors for its role in the future. But I just don't support the logic that, people who point to the all of the above strategy, or for instance, the initiative that came out of COP28 that the US spearheaded, that we should triple nuclear energy by 2050. That's a kind of arbitrary and irrational approach, and just doesn't, grapple with the hard reality of trying to make that happen in any kind of safe and economical way. So you just have to approach it without ideological blinders on.
Thank you.
Great, thank you. Bob Fader, I see you have a question in here.
Yeah, if fusion power was ever to become a reality and widely used, do we have any idea what the potential health problems with that might be?
Yeah, I mean, it's a bit of a myth that, fusion has a different safety profile than fission. But it's a myth that some people are maintaining, that it's essentially risk-free. The difference is that the radioactive waste generated from fusion don't have high concentrations of these very long-lived isotopes like, plutonium, or relatively small amounts of plutonium in the waste. But when a fusion plant is operating, that intense neutron source just turns everything, makes everything around it radioactive. And it's anytime you're containing a very high energy source and, at a high energy density, at high temperatures and pressures, you have the potential for an explosion. And if you do have an explosion, a fission power plant, that radioactive material, everything around it, the shroud and structures that have been irradiated, are going to disperse and will cause a radiological event that could be comparable to something like a fission accident. There are studies, some of them look pretty bad. Also, because fusion, at least the easiest way to do it, involves large quantities of tritium. Tritium is a radioactive isotope of hydrogen. In high concentration, it's very hazardous. And the amounts of tritium that would have to be produced and used at a fusion power plant are very significant from the public health perspective. So it's definitely not the same as fission, but you can't dismiss those potential risks either.
Thank you.
Thank you. Just want to be mindful of time here. It's a few minutes after 7. We have one last question in the chat, if that's okay, and then we'll wrap up. Bob, you had a question about 4th generation reactors.
Yes, I do. This is something that Bill Gates talks about in his book. And I also read it and just said, oh my gosh, what a wonderful idea. But since a lot of the accidents revolve around the cooling, these newer generation reactors, which are smaller and cooled with liquid metals like sodium, is that necessarily safer? And will that cooling that way without pressurized water, is that going to result in fewer accidents? And also, is the fact that they can burn already, or not burn, but use uranium that's already been partially depleted, does that make that uranium, when it's stored for the future, safer if it's been further depleted? I mean, it's probably a stupid question, but that's another thing that they sort of really stress, I think, in Bill Gates' book.
No, it's not a stupid question, because first of all, I don't think Bill Gates himself understands the reactor that he's paying to develop. Unfortunately, liquid metal cooled fast reactors are not by any stretch of the imagination safer than light water reactors. In fact, they have risks. One major difference is that they are much less stable to small perturbations. So you can have, Chernobyl was caused by a massive reactivity transient, essentially a huge power increase over a short amount of time. Light water reactors don't have that property, but fast reactors could. If the sodium boils, you could have a large power increase like Chernobyl. And so the people who advocate for fast reactors have been trying to cover that up for decades by citing other factors that they claim will make them safer. In my assessment, no, liquid metal cooled fast reactors are much more dangerous. And the idea of this other claim that somehow, if I'm characterizing it, that nuclear waste can be recycled and burned up. You can burn up those long-lived components, and what you have left over is much safer to dispose of. That's another pipe dream. In fact, the process of actually trying to extract those isotopes that you would want to recycle in a nuclear power plant, like a fast reactor, that's an extremely damaging to the environment. Also, there's significant proliferation concerns associated with it because you're extracting plutonium primarily, which is a nuclear weapons material. And it's not even very effective if you try to recycle. In fact, I have a study, I can send the link around if you want, that shows that it would take maybe tens of thousands of years of continuously operating, recycling the fuel for these types of reactors before you actually made a dent in all the waste that we have today. So it's not realistic. It's dangerous and probably worse than the default option, which is directly disposing of spent nuclear fuel in a geological repository. Unfortunately, there's no program right now for developing that. So we're just stuck with the waste above ground. But even if you had a perfect recycling technology, you'd still need that repository, which is still way in the future. So there's no free lunch really with nuclear power.
Thank you.